At 0302.29 UTC on May 21st, 2019, twin detectors on opposite sides of the United States, along with a third in Italy, registered a violent tremor in the fabric of spacetime itself. A gravitational wave, a distortion smaller than the width of a proton, had crossed roughly 17 billion light-years of empty space to reach us. Within hours, scientists knew they were looking at something extraordinary, but within days, they realized something else entirely. The signal did not behave the way it was supposed to. It was too short. Half of it was simply missing. For 6 years, this anomaly, later catalogued as GW90521, sat as an unsolved irritation in the back of astrophysics. Then, in September 2025, a team of Chinese researchers published a paper so audacious it sent ripples of its own through the theoretical physics community. Their claim was this: what if the missing half of that signal never happened in our universe at all? What if we had just detected an echo leaking through a wormhole from a black hole collision happening somewhere else entirely in a universe not our own? I'm Alex McCone, and you're watching Astrum. Join me today as we break down the physics of wormholes, untangle the mind-bending relationship between quantum entanglement and space-time geometry, and examine whether we really eavesdropped on an echo from another universe. When the Laser Interferometer Gravitational-Wave Observatory, or LIGO, first detected the signal that would become GW1990521, researchers realized something exhilarating. If their interpretation of the colliding black hole's size and mass was correct, they had just made the first detection of an intermediate mass black hole in human history. Until then, astronomers had only observed two categories of black hole: stellar mass black holes, generally under 65 solar masses, and supermassive black holes, monsters measuring hundreds of thousands to billions of times the mass of our Sun, typically lurking at the centers of galaxies. The mathematics had always predicted a third category should exist in between: intermediate mass black holes weighing somewhere between roughly 100 and 100,000 solar masses. Computer simulations agreed, but nobody had ever directly observed one, until this gravitational wave hinted that one might finally be out there. The signal appeared to be the echo of two black holes colliding, one measuring roughly 85 solar masses, and the other around 66. Together, they merged to form a remnant black hole about 142 times the mass of our Sun. If you do the math, that means the equivalent of 8 to 9 entire suns worth of mass was instantaneously converted into pure gravitational energy and radiated outward in a fraction of a second. The event was formally announced by LIGO and Virgo on September 2, 2020, and instantly became the most massive binary black hole merger ever recorded, arriving from a source roughly 5 billion parsecs away, at a redshift of around 0.8. As exciting as that already was, in 2025, a research team led by physicist Qi Lai, working at the Hangzhou Institute for Advanced Study under the University of Chinese Academy of Sciences, took a much closer look at the shape of the signal left behind by GW1990521. What they found puzzled them. No matter how they sliced the data, this signal simply did not resemble a typical black hole merger, so they began asking what else it could be. Normally, when two extraordinarily massive cosmic objects collide, whether neutron stars or black holes, that collision sends tiny ripples through space-time radiating outward in every direction. Occasionally, these gravitational waves eventually wash over Earth, where we can detect them using ultra-sensitive ground-based laser interferometers, most notably LIGO in the United States and Virgo in Italy, with a third detector, CAGRA, now also operating in Japan. Depending on the exact shape and character of the signal we receive, scientists can work out what kind of event produced it, how far away it happened, and roughly how massive the colliding objects were. When two black holes merge, the resulting signal moves through three distinct phases, each with its own recognizable signature. In other words, scientists can usually tell that a gravitational wave came from a black hole merger simply by its shape. The first of these three phases is called the inspiral. As two black holes circle one another, they continuously radiate away energy as gravitational waves. Because they are steadily losing energy, their orbit gradually tightens, which makes them move faster, since the gravitational pull between them grows stronger as they close the distance. The faster they move, the more energy they radiate, creating a runaway feedback loop, spiraling closer and closer, accelerating the entire time. What does that mean for the resulting signal? It steadily climbs in both amplitude and frequency as time passes. Converted into an audible sound, it produces a rising tone, not unlike a bird call sweeping upward in pitch, which is exactly why astrophysicists refer to black hole collisions as producing a characteristic chirp. The second phase is the merger itself, the precise moment the two black holes actually collide and become one. At this instant, the amplitude of the signal reaches its absolute peak, marking both the highest point of the waveform and the most intense, rapid compression of spacetime involved. This is immediately followed by the third and final phase, the ringdown. It takes a brief period for the newly formed black hole to settle down and stabilize. Initially, it is wobbly, distorted, and irregular in shape, before eventually relaxing into a smooth, stable sphere. Throughout this settling process, the black hole continues emitting gravitational waves, though in a noticeably different form than before, fading tones rather than a rising chirp. In the specific case of GW190521, the ringdown phase occurred simultaneously across two distinct frequencies, a fundamental tone at 63 Hz and a secondary tone at 98 Hz, both fading out entirely within roughly 26 to 30 milliseconds. Researcher Colin Capano of the Albert Einstein Institute has compared this to a bell being struck, producing a spectrum of overlapping, fading tones that together encode information about the size and shape of the bell itself. Carefully analyzing the ringdown phase of a black hole merger can reveal detailed insights into both the mass and spin of the newly formed black hole, as well as clues about the two progenitor black holes that created it. That is exactly what a typical black hole merger signal looks like. But GW19900521 was different. This particular gravitational wave signal was almost entirely missing a clearly identifiable inspiral phase. Scientists only detected the merger and the subsequent ringdown, with essentially nothing recognizable coming before it, a signal lasting well under 1/10 of a second in total. And this glaring absence is precisely what led Lai and his team to propose their genuinely outlandish hypothesis. What if this signal was actually the echo of a black hole collision that occurred not in our universe, but in a parallel one entirely? A signal that reached us only after traveling through a wormhole connecting the two. Wormholes might sound like pure science fiction, but they remain a legitimate mathematical possibility within general relativity. As Albert Einstein worked through the equations of general relativity in the 1930s, the concept of space-time bridges arose naturally as a hypothetical geometric feature of the universe. Later, as physicists throughout the 1980s speculated seriously about traveling from one distant region of the cosmos to another, this early theoretical bridge evolved into the concept we now popularly call a wormhole. So what exactly are they? Essentially, a wormhole functions as a theoretical shortcut through spacetime, a tunnel connecting two extremely distant regions of the universe, or conceivably even connecting entirely separate parallel universes. We have never directly observed a wormhole in reality, but if we somehow did stumble across one, it likely would not resemble the flat, darkening tunnel most people picture. Instead, a wormhole would probably appear as a spherical, three-dimensional window, offering a warped, distorted view of whatever lies on the far side. Much like a black hole, it would likely be surrounded by intense gravitational lensing, visibly bending the starlight around it. From this point forward, we are moving into genuinely hypothetical territory. So keep in mind, much of what follows remains contested and debatable. There are several theorized varieties of wormhole, but let's start with the original, the Einstein-Rosen bridge, first described mathematically by Einstein and physicist Nathan Rosen in 1935. This is a geometric structure featuring a black hole on one side and a white hole on the other, opening into a different universe. Here's the basic idea. As you likely know, matter can enter a black hole but never escape. Once an object crosses the event horizon, there is no return. A white hole is the mathematical opposite, a structure where matter and information can only exit outward, never fall inward. The underlying Einstein field equations that define black holes happen to be symmetric with respect to time. That means the same mathematical solution describing everything collapsing inward toward a singularity in the future can technically be reversed. In that reversed scenario, the singularity effectively represents the past, and matter is ejected outward from what we call a white hole. The white hole's event horizon would function as a boundary nothing can cross inward, which is why white holes are often described as black holes running backward through time. The Einstein-Rosen bridge is theorized to connect a black hole with its corresponding white hole through this one-way structure. The trouble is, the underlying mathematics strongly suggests this structure would be catastrophically unstable, collapsing almost instantaneously, so quickly that not even light would have time to pass through before it pinched shut. So if the GW19900521 signal could not plausibly have traveled through a classic Einstein-Rosen bridge, what other kind of wormhole might it have used instead? In 1988, astrophysicists Michael Morris and Kip Thorne proposed a theoretical method for making wormholes genuinely traversable. Thorne later served as a scientific consultant on the film Interstellar, and eventually won the 2017 Nobel Prize in Physics for his foundational contributions to the LIGO detector, and the first direct observation of gravitational waves in 2015. So let those credentials lend some weight to the admittedly bizarre theory that follows. Morris and Thorne suggested the narrow choke point, or throat, of a wormhole could theoretically be propped open against gravity using a kind of exotic scaffolding, making passage through it physically possible. However, this scaffolding would require an entirely theoretical category of material known as exotic matter. Exotic matter is not the same thing as antimatter. which does possess positive mass and is a genuinely observable substance that scientists routinely produce in particle accelerators. Instead, exotic matter refers to material with deeply unusual properties, such as negative mass, negative energy density, or negative pressure, meaning it would behave in strange, counterintuitive ways. These two well-established theories therefore seem to directly contradict one another, creating what physicists now call the firewall paradox. This is precisely where things unexpectedly began to fit together. The ER equals EPR conjecture appears to offer a way out of this contradiction. Back in 1974, Stephen Hawking postulated that black holes experience quantum effects near their event horizons, causing them to slowly emit what became known as Hawking radiation, gradually evaporating away over incomprehensibly long timescales. The lingering question has always been whether that escaping radiation carries any genuine imprint of what originally fell in, or whether it is just meaningless random noise. If the Hawking radiation particles escaping outward are quantum entangled with particles still trapped inside via a hidden wormhole, then information was arguably never truly lost. If the interior and exterior of a black hole share a quantum connection through this hidden bridge, the missing information becomes recoverable in principle by studying the Hawking radiation itself. But there remained one significant problem with ER equals EPR. It had only ever been mathematically demonstrated for an extremely idealized scenario: two black holes sitting in perfect thermal equilibrium. Real black holes are nothing like that. They are messy, violent, and chaotic, constantly bombarded by infalling matter, radiation, and unpredictable quantum fluctuations. If ER equals EPR only functions properly for perfectly neat, idealized black holes that do not actually exist anywhere in the real universe, it would not represent much of a genuine solution. So, in 2025, a team of researchers set out to test whether this conjecture could hold up under more realistic conditions. They built a detailed model of a pair of deeply entangled black holes connected by an Einstein-Rosen bridge, known formally as a complex EPR pair. Starting from an idealized wormhole, smooth and symmetrical on the inside, they progressively scrambled the entanglement between the two black holes, making the system increasingly chaotic. What they found surprised nearly everyone involved. Even once the entanglement became genuinely messy and random, the wormhole remained a remarkably predictable, stable tunnel throughout. It grew longer, bumpier, and more deformed, developing lumpy segments along its length, earning the structure the informal nickname the Einstein-Rosen caterpillar. Crucially, it remained a geometrically stable, genuinely traversable structure the entire time, where classical gravity continued to hold. Perhaps most intriguingly, in none of their typical models did researchers ever encounter anything resembling a firewall at the event horizon. So coming back to our mysterious gravitational wave, for it to have genuinely traveled through a wormhole, two things would need to be true. First, wormholes connecting entangled black holes would need to be physically real and stable enough to transmit a signal, something the Einstein-Rosen caterpillar research seems to demonstrate is at least a legitimate possibility. Second, information itself would need to be capable of traveling through such a structure. Remarkably, back in 2022, a Harvard-led research team demonstrated something close to exactly that. In an experiment that genuinely sounds stranger than fiction, they constructed a holographic wormhole inside a quantum computer and successfully transmitted information through it. Before your jaw fully hits the floor, let's unpack what that seemingly impossible sentence actually means. This experiment traces back to physicist Daniel Jafferis at Harvard, who in 2016 calculated that if you could take two entangled quantum systems and couple them together in precisely the correct way, you could perform an operation on one side, which, according to ER equals EPR, should physically hold a wormhole open and push genuine information through it. The remaining question was whether anyone could actually build and test such a system in practice. 6 years later, a team led by physicist Maria Spiropoulou at Caltech did exactly that. Working with Google's Sycamore processor, a state-of-the-art superconducting quantum computing chip, they simulated two entangled quantum systems that, according to the rules of ER equals EPR, should theoretically be connected by a wormhole. Here is precisely what happened next. A single unit of quantum information, a qubit, was injected into one side of a two-sided quantum system via a single particle. That encoded information then diffused outward from that one particle, spreading across all the other particles on that side of the system, much like a drop of ink dissolving into a glass of water. The team then performed a specific rotation across all the qubits involved, equivalent, in the gravitational picture, to sending a pulse of negative energy through the wormhole, effectively propping it open with theoretical exotic matter. Eventually, that same encoded information re-emerged on the opposite side of the quantum system entirely. It had somehow reconverged, refocusing itself from a diffused state back down onto a single specific particle, the direct entangled partner of the original particle that had carried the qubit into the system in the first place. In other words, the team had successfully sent a piece of information into a quantum tunnel and reliably retrieved it intact on the other side. Spyropoulou later said the moment felt comparable to seeing the very first data confirming the discovery of the Higgs boson. That said, the wider physics community quickly urged caution. Some independent analyses argued the underlying quantum model used was still far too simplified to genuinely capture the true complex properties of a real astrophysical black hole, meaning the demonstration should not be interpreted as a literal, physical, holographic wormhole. Even so, the team had convincingly shown that a quantum system governed purely by the rules of quantum mechanics could, in principle, behave in a way mathematically identical to a wormhole described by gravitational theory. The underlying physics at both the quantum and gravitational scales appears strikingly similar, even though the observable physical reality looks completely different in each case. So, returning to that strange gravitational wave that started this investigation back in May 2019, if it truly did travel to us through a genuine wormhole, this quantum computing experiment is the closest thing we currently have to a proof of concept that such a journey is at least mathematically and experimentally plausible. But can we conclusively say whether it actually happened? Knowing what we now understand about wormholes, quantum entanglement, and the flow of information, let's reassess the original paper that launched this journey. Keeley and his research team ultimately proposed that gravitational wave signal GW190521 represents the echo of a black hole merger occurring within a separate parallel universe. In that other reality, two black holes would have spiraled together and merged in the ordinary way. But instead of simply forming a larger black hole, the collision instead created a wormhole, one end anchored in that parallel universe, the other opening directly into our own. We never detected the inspiral portion of the signal because it remained confined within that parallel universe. But as the subsequent ringdown phase radiated outward, some fraction of those gravitational waves traveled down through the connecting wormhole and emerged on our side of the divide. We already know it is theoretically possible for a wormhole's throat to be held open using negative energy, and for information to successfully pass through such a structure. So this hypothesis is not quite as outlandish as it might initially seem. The researchers go further, attempting to explain why the signal was so short, lasting roughly 1/10 of a second. They suggest we may have detected only a single isolated pulse, rather than a series of progressively weaker echoes, as one might expect from a standard ringdown, either because the wormhole rapidly collapsed after forming, or because subsequent echoes were too faint for our detectors to register. This cannot be entirely ruled out, since there remains a non-zero possibility it accurately describes what happened. But the authors admit that, even accounting for the missing inspiral phase, a conventional binary black hole merger in our own universe still fits the data better than their wormhole explanation. Even so, this study carries genuine scientific value beyond being an entertaining thought experiment. It matters because it gives astronomers a concrete, testable framework for evaluating an exotic idea against real detector data. The Harvard-led quantum computer experiment demonstrated that wormhole-like dynamics could be mathematically real and experimentally testable in a lab. The Einstein-Rosen caterpillar research shows wormholes connecting entangled black holes are not purely science fiction and can genuinely emerge from the mathematics of quantum chaos. Together, these findings, combined with the broader ER equals EPR conjecture, build an increasingly compelling case for a mathematical connection between quantum mechanics and general relativity, one that real merging black holes like GW190521 let physicists actually test. Looking ahead, our ability to detect these events is only going to improve. Since resuming operations in 2024, LIGO and Virgo have run with roughly 30% increased sensitivity, now allowing scientists to detect a black hole merger somewhere in the universe roughly once every 2 to 3 days. Given that we have only been capable of detecting gravitational waves at all for barely a decade, this field remains very much in its infancy. As our models and technology continue improving, it remains entirely possible that scientists will eventually conclusively confirm whether wormholes genuinely exist, and perhaps, one day, even find a way to send something through one. For now, though, the honest answer is that we simply do not know. GW190521 remains most likely, according to the researchers' own analysis, an ordinary, if unusually massive, black hole merger within our own universe. But the fact that a wormhole explanation cannot yet be ruled out, and that quantum computers have already demonstrated something eerily similar to a working wormhole in miniature, means the question refuses to fully go away. Perhaps one day, with more sensitive detectors and sophisticated models, we will finally know whether humanity briefly glimpsed a flicker of another universe, or whether we simply misread the signature of two exceptionally large black holes colliding in a way we had never quite witnessed before.